All right, let's try this with you. So, black background, white screen, or white background, black writing?
Black writing.
Black writing?
Yes. Yeah.
Okay, let's try.
And
Turn off that light.
Yeah.
Yes, I will do. In fact, and you get to see my horse. Great. Let's see. Well, let's see if this works. No. Oh, that's not good. Pardon me?
maybe it's still set on white, right?
That is probably what happened. Good. Any better?
Yeah.
People in the back? Woo! Okay. I stole my son's tablet for this. He's going to be very unhappy since you're also happy. I may have to go and get another one. This is a temporary load from him. And he's only 8. He doesn't, you know. Okay. Okay. So today I'm going to talk about, so we've talked about how the plan for a divide and conquer strategy is to try and break things down into pieces, maybe roughly the same size, and then recurse. And we talked about how that gets you down to n log n, and it's very hard to get any further than that. We also talked last time about a strategy called decimation allows you to get even further down to linear time for a problem, with the idea being that every step you can spend linear amount of work, but you have to throw away a constant fraction of the input. And that constant fraction could be 0.1%, could be 0.2%, could be 0.0001%. It doesn't matter. It has to be a fixed constant fraction. It can't be 1 item or 2 items or 3 items. And so if you can do that, then you can solve a problem in linear time because of the way the reference works, and you can prove that. But what we'd like to see are some good examples of problems where this happens. We've seen an example of how to do decimation with binary search, because you have, at every step, you do a constant amount of work and you throw away half the input. And if you imagine what the recurrence will look like in your head, P of n is equal to P of n over 2, that's half the input plus a constant, which is the amount of work you did to figure it out, you get log n. But the thing we're going to look at today is where you do a bit more work, you do a linear amount of work, and you still get linear time. And the problem is going to be selection. Okay? So the problem of selection is wait, that's not right. So, given n items, find the kth largest. Okay? This is the problem of selection. Of course, if you are trying to find the median, then that's just a special case of this problem, where k is equal to n over 2. Right? So if k is equal to n over 2, then you get the problem of median find. Okay? And that's what we want to do today. We want to learn to find medians, and we're going to use a general algorithm for k selection in order to solve it. And this is, by the way, another important point. Sometimes when you want to solve a problem, the trick is to make it harder. Then it becomes easier. Because you essentially are in a much bigger space that you're going to solve, and that allows you to solve your actual problems as a special case. So another standard trick in that. Okay. So let's say we have let's say we want to do this via some kind of decimation or dividing strategy. Right? So we want to be able to say, okay, in order to find my median, I'm going to do something, I'm going to throw away a bunch of stuff, and I'm going to recurse. And as we've seen before, as long as you figure out how to throw stuff away and how to recurse correctly, you're done by recursion. So let's say let's be concrete, let's say we have a collection of numbers here. So someone shout out some numbers to me. 1.
6.
25.
What?
25.
Pi.
28. 12.
42.
Pi.
Euler's constant. Avogadro's number.
Oh, you challenged me. Okay. 6.0 times 10 to the minus 23?
Close enough.
6.27.
6.07?
6.27.
Right?
6.27.
6.27 times 10 to the minus 23. Okay. Okay.
027.
Sorry, I only have 32 minutes.
027.
Use single precision.
I'm a theoretician. We don't deal with numbers. Okay, so we have a bunch of numbers, we want to find the median, right? So what is the median? Tau is 2 pi, by the way. I guess there's at least one tau snob. Tau is 2 pi, for some reason there's this whole campaign to make tau a better number than pi. That's not even what it is. So let's see, what is the median of these numbers? There are 10 numbers, which makes it easy. So let's see which is the 5th largest. So there's 1, there's E, there's pi, there's 5, and there's 5. Is that right?
Yeah. It's 5.
Sorry? 5 is twice, that's fine. That's okay. Right? So I think 5 is the median in this case.
Which 5?
No,
There are 2 5s.
the other one.
This tau.
2 pi.
So what we'd like to do, okay, so how would we go about designing an algorithm? And again, the goal is not to come up with any old algorithm, is to come up with one that focuses on doing it by recursion. Not because I like walking on my hands like that in my back, but because we're trying to sort of see, if you have a general problem, that's how you would do things. You say, okay, let me try this tool, and let me try that tool. And a tool right now is decimation or recursion. You were saying something about sorting. You could sort. It would be very easy. Once you sort, you just pick up the middle element. What's the problem with sorting?
You're doing extra work.
So I hear 2 comments. You're doing extra work and it's taking n log n. They're both correct. You're taking n log n time, which is a big no-no because your idiot professor said you have to run in linear time. And you can't use n log n. But more importantly, and this is a subtle point, you're actually doing a lot of work. You're not just find the median. You got everything in rank order. And that's often, but not always, a sign that maybe you could do better. That maybe I'm doing too much work. Sometimes that's not true. Sometimes, in fact, they're equally hard. But sometimes it's a sign that, okay, maybe do I really need to order everything just to find the one that we do? Because intuitively, if I want to find the median, I don't care if the stuff below it is sorted. I don't care if the stuff above it is sorted. I just need to know this. So how might we think about how to do this? Yes?
What if we use something like a binary tree?
You use a binary tree.
Like stick an element in, and then anything that's greater on it, put it in one branch, and it's less than put it in the other branch.
Yes.
And mess with the tree until.
How long does it take to
it's
build a
balanced.
binary tree?
Hmm?
How long does it take to build a balanced binary tree?
I have no idea.
If you build it as a heap, it's linear time. Then to pull each element out takes n log n. Takes log n time. So you spend n time to build it, to take n log n time to actually retrieve the median. Or if you build not a heap but a red black tree, it will take n log n time to build it. So, yes. Sorry, your name?
Victor.
Victor? Okay.
If our goal is just for linear time, why aren't we just going through the whole thing looking one by one?
Very good. Why don't we just go through the whole thing looking one by one? Tell me how you do it.
So you would keep account of how many things you've seen, and then how many.
So, okay. 1, 2, 3, 4. Okay, now what do I do?
And then at each step you could compare with your current selection. So you would take the first item.
Okay, so take the first item 1. Okay, now what do I do?
So I've seen one item out of one,
Yeah,
and that's fine.
fine, good.
And then you go to the next one,
5.
and then you would also, I guess, keep track of how many things less or.
Sure. So now there's one thing above my 1. Now I come here, now there are 2 things above 1. There are 3 things above 1. And I go all the way to the end, and I know that in fact everything's above 1. So I know 1 is not the answer. And I've spent linear time. Good. Now do it. This is very good. What you've done so far is very good. But we're not quite there. We're not quite there yet.
And I guess
Pick another pivot.
since you have the counts, you could.
Sorry, go ahead.
So since you have the counts, you could, while you're doing it, maybe keep track of which ones are larger and which ones are smaller.
We just did that, right? We know which ones are bigger than 1, which ones are smaller than 1.
Yeah. And then we can throw that.
Oh, wait, a lot of people talking. You're next.
Pick a pivot at random. Arrange the items.
Something at random. Now you're being clever. That's why only one rule this class. Don't be clever. No, I'm serious. Don't be clever. Sometimes being clever gets you too far ahead, and then you realize you get stuck, and you just need to be not so clever. There's an argument for doing that, and we'll get to that in about 12 lectures. So you're about 12 times more clever than me, so hang on. Yes, you were going to say something. Your name?
Deepshika.
Deepshika, okay.
We can have an array of 5 numbers. And
You're being clever too. Yeah, you're being good. I don't want, there are no clever people in this class. Please. Because, okay, here's the reason why. If you know the answer, it's great. And this is a very well-known algorithm. I would not be surprised if half of you knew the answer already. That's not the point of what I'm doing. If I doesn't tell you the answer, go read it. I mean, you don't need me for that. I'm trying to get you to the process of getting the answer. That's much more important than the answer itself. Because tomorrow when you get this new problem, there will be no answer for it. All you have is the process. So I want the process, not the answer. So if you know the answer, please don't answer.
so I don't know the answer. I just came up with it.
You just did. Even better. Now tell me.
So what I thought was we can have an array of 5 numbers, and
Fine.
we can, like, because we know all numbers are 10. The
10
total
numbers.
is 10.
Yes.
So we need the 5th number.
Yes.
That is so we can keep the largest number in those 5, an array of 5 numbers,
Yes.
and the one which is the smallest in that would be the answer.
I see. So I unjustly maligned you. That's a good idea. That is not being too smart. That's a very clever idea. Okay. So good. So you keep the top 5 numbers because
Yeah.
you want the
Because
goods
we
half.
know-
And then you scan the array till you fill in that. Good. How long will this take? Let's say now I have n numbers and not 5. Or not 10. So now you want the top n over 2 numbers. Yes. No, it's not sorting.
It's not sorting.
It's not sorting. It's comparing, but you get the top n over 2 numbers. You may have to scan the area and put them in one by one, right? How long will that take? For each of n over 2 numbers, you have to scan the area.
Can you do it in linear time?
Tell me.
We compare 1 with 5, and we know that 5 is bigger.
Okay.
So we keep it in.
So 5 wins.
No, we keep it in the
In the array.
In the array.
Right.
And then we compare. Since we already know that 5 is bigger, we compare 5 with 7.
And then 7 wins. So 7 goes in the array too. But 5 stays.
Yeah, 5 stays.
Yeah. But that way 1 should stay as well, right? Because so far I've only seen 3 numbers. They could be the 3 numbers.
Okay, yeah, we can do that. And
Yeah. So good. So we start the array. 1 goes in the array. 5 goes in the array because it's bigger than 1. 7 goes in because it's bigger than 5. 6 goes in because there's a slot available.
We have
25
to
goes
keep
in.
track of the smallest number.
Sure, 25 goes in because that's available. And now next 5 comes in. Someone has to, no, 5 is too small.
Yeah.
We'll throw it out. Pi is too small. We'll throw it out. Tau is too small. We'll throw it. 42 is big. So someone gets thrown out there. We throw the smallest
We
one,
can
which is
throw
1.
the smallest one.
Yeah. And then E goes in. And that will throw out nothing. Sorry? It won't get in because it's smaller. How long did this take? It's not linear time. Because you had to go search in this area to find someone to throw out. At the very least, you're going to spend log n time. It could be even worse if you're not careful. But at the very least, you spend log n time. But this is good. You want to keep an array and you want to scan them in, but now again, we're stuck with this whole, it takes log n to find them. Yes?
We scan the array,
Yeah.
but at the same time, let's say we take 1.
Yeah.
We divide it into 2 groups. And if 1 is not the median.
Yeah.
If 1 is, but we know where 1 is with the median. Well, if in n elements we would know whether it's somewhere around third or whether it's below n by 2 or above n by 2.
Yeah.
If it is below n by 2, I throw away the one which is above n by 2. I throw away half of the array in my next recurrence.
But you have it by 2?
Because I don't
So you
have.
start with 1. You start with 1 as your guess.
I start with 1.
So I know that everything is above 1. There are 9 elements above 1. There are 0 elements below 1. Now wait.
Then my next recurrence will have again n elements.
It'll have, would you keep 1?
1 is not the median, no.
So you can throw it away.
I can throw it away.
So you make progress.
Yes.
Good. So one idea is to say, let's look at 1. Yeah, it's the first number. Let's look at it. We scan the entire array, taking linear time, at the end of which we know exactly what the rank of 1 is. The rank is a position in the array. So 1 is, in fact, has rank 0. Or 1, whichever you, depending on if you're a MATLAB or a C. So, okay. So we know that this is not going to be the median. So we can throw it out. Okay. Let's say instead that our number was, I don't know, 25 that we picked to start with. So we scan the whole array, we figure out there's 1 above it and there are 8 below it, right? What do we do now?
Throw away 5 and 25 and 40.
Throw away 25 in the stuff above it and do the stuff below. So this is great. We now have a recursive algorithm, right? So we're saying that we want to take any element, figure out its rank, and based on that go one side or the other. Either take the stuff below it or the stuff above it, right? So what would our recurrence look like? So our recurrence, so let's say we say pick an element, find its rank. Oh my god, I use an apostrophe, it's terrible. In that case, I'm just to warn you all, I'm going to go to the next page because that causes some consternation. Okay, what happens now?
So picking an element is a random.
No, that would be clever. We're not allowed to.
Yeah, so this is what I'm asking.
No, arbitrary. So along with having hallucinations about recurrences, the other thing that I hope you go away from this class is an understanding of the distinction between arbitrary and random. And I'll harp on this more when I talk about randomized algorithms. But I mean arbitrary. I mean any element. An element chosen to you by your worst enemy who wants to make algorithm really fast, really slow. Okay, arbitrary. I'm not picking. What would this recurrence look like? So if I chose the element and I don't know what its rank is, let's say its rank is k, right? If the value of k is more than over 2, then I have to recurse in the stuff below, right? And look for the element of rank what? N over 2 minus k, right? If it's above, right? Then I look for the element of rank k minus n over 2, because I've taken off some of the stuff on the side. So if element picked has rank k, then recurs, so the 2 cases. So if k is less than n over 2, then you recurse above, looking for rank n over 2 minus k. Is that right? Oh no. Will it be n over 2 minus k?
Yes.
Okay. Because I throw it here. And if it's if k is more than n over 2, and you recurse below, looking for rank n over 2 as before. Not n over 2, sorry. It'll be n over 2, but the set is of smaller size, so be careful. Your set of size is n prime, but you just have the fixed rank n over 2. Okay? What if the rank is equal to n over 2?
And you found
We're
it.
done. Trick question. So, yes, Matt.
What does above and below mean if the list is not sorted?
What did I say? I said I'm going to find the rank of the element I just picked because I'm going to scan the array. I would say this element is the 7th highest in the list. Right? I can compare the number 7 to the list size divided by 2. I'm not sorting. That's the thing. I didn't have to sort to figure out the rank of any individual element. Because I can look at this element, compare it to everyone else. Okay, you're bigger or smaller, you're bigger or smaller, you're bigger or smaller. They're not sorted, but I know my rank. Does that make sense?
Yes.
Okay, yes.
So you have a space that kind of says which element is higher, which element is lower?
I just keep 2 counters. Yeah, or
For each element.
well, algorithmically, what I'm going to do is I'm going to take this pivot, and I'm going to basically figure out the inefficient way to do this is to do this one pass and figure out its rank, then rearrange the array to create a space that k position is there, so I have the 2 parts on either side. So I just do one more scan where everything that's small in this I put on one side and then figure out what the other side. There are more efficient ways of doing that, but for now we'll just pretend that's what we do. So at the end I have the array segregated, rewritten into 2 parts, and this guy's in. Oh, this guy's at the beginning of the 2 parts, and I have 3 parts. So I can recurse on them. I have a pointer. Okay, what is the recurrence relation that describes this process? The recurrence relation that describes this process will be something like the running time on n items is equal to some constant times n, because I have to scan, plus the running time on some subset of what size? Well, if the element is less than n over 2, then I work on n over 2 minus k. If k is more than n over 2,
You always throw away k elements, you're saying it should be n minus k.
we always throw away k elements. Do I always throw away k elements? Yes. No, sometimes I throw away n minus k elements. Yeah, right. So either my running time looks like this, or it looks like this. One of the two things will happen, not both. Right? This or this. And we don't know what k is, because we picked an arbitrary element. Okay. Can we analyze this vectors? If we had to analyze, if I just gave this to say for arbitrary k, you have to do a worst case analysis. What is the worst case situation? Now you know how references work. What is the worst case situation for this kind of reference? Okay, wait, let's say that side. Yeah.
Every time you pick the highest number.
So you only lose one element at a time. Right. So k is, you always pick that one of these two numbers is 1. What's the right time going to be if that happens? So you go n, you'll go n minus 1, you'll go, no, it's no choice. It will be n, it will be n minus 1, n minus 2, n minus 3.
Yeah,
That's going to be, no.
Minus 1 and minus 1.
That's n times n minus 1. This is n plus n minus 1. It's just n squared. So n plus n minus 1 plus n minus 2 plus n minus 3. Imagine, remember, integrating x. If you integrate x dx, what do you get? X squared over 2, right? That's your, again, handily, but it gives you the sense of where this is going. So n squared, that's no good. We know what we want. We want what? We want k to be balanced. But we don't even need balance. I mean, n over 2 would be great, but we don't need that. Remember what I said for decimation? We need some constant factor. So k, all k has to be is some constant fraction of n. It could be n over 2, which would be great. Then we found the mean already. It could be n over 3, it could be n over 4, it could be n over 10, it could be anything, as long as it's a constant fraction. So our problem of solving the median has reduced to, how do I guarantee to find an element with linear amount of work that is guaranteed to split my sets into sets that are not too skewed, that there's at least a constant fraction. It does not have to be half, it has to be something. So we've taken the original problem, find median. We've made a recursive formulation, find median in smaller set. And now our whole strategy is reduced to the following question, finding this good element, which I'll call a pivot. Finding a good pivot. You want a pivot to be somewhere in the middle. And as we'll see much later on, oftentimes when you have a question like this, the answer is to do it randomized. Just pick it random and it usually will work. But we don't know that yet. So we're going to work harder to try to do this exactly. How would we go about it? And again, here's where we're going to use recursion over again. And this is a bit, I mean, in some sense it's clever. It's a thing that I disallow this block. It's a clever trick. In the sense that I'm not sure I can explain to you how to get there. Okay? And that's why it was a cool result when it first was shown that you could do median linear time. You were very surprised. You didn't expect this. So in that sense, it is a little surprising that it works. So let me just tell you how it works, and then we'll wonder why it works. Okay, I should be able to export all this and put it up on the screen. There's much in there, but I'll have it there if you want it. So the algorithm is going to work as follows. So we're going to pick a number, and it's going to be 5 as it turns out, which is why I jumped around. And like I said, I was unfair. So let's pick the number 5, and we're going to imagine a number we're going to reorganize the numbers mentally, not algorithmically, but mentally in groups of 5. So we're going to do this. So we're going to have the numbers here. This is the first group of 5. This is the next group of 5. All the way to the end. Okay? So of course there are going to be n over 5 of these groups. Again, do this conceptually, we're not actually rearranging stuff. Just imagine your array, take the first 5 elements of the first group, and so on. Okay. I am going to find the median of each group of 5. And that's why I picked 5. I want an odd number. Okay. So I'm going to pick the median of each group of 5. But I can do this in constant time. Right? It's only 5 elements. So I mark off the first median, which is somewhere here. Well, that's where it should be. The second median will be here, and so on, and so on, and so forth. How many medians of this kind do I have? I have n over 5, right? 1 for each group of 5. The next thing I'm going to do is take the median of these medians. Now that's kind of why? Okay, so we're going to do that. So let's say the median of these medians, is going to be somewhere this one. I claim that this is the element we should use to separate things. And this is guaranteed to separate things out nicely. So I've taken one problem, how to find a pivot, and made it into 2 problems. How long will it take to find this special element? And why on earth should it work? Right. 2 questions to be answered. How long and why? So let's answer, I don't know, which you want to hear first? Anyone? Why? Yes, that's a more bizarre. So here's the clever thing about this. I claim that this element is a pivot, which means I claim that its rank is not too far to one side or the other. Right? Its rank is not 1. It's never going to be the smallest element. It's never going to be the biggest element. In fact, I'm going to make a particular claim about this element. That the rank of this special element is greater than equal to 3 over 10 of n, and it's less than equal to 7n over 10. It's somewhere in that range, between 30% and 70%. So if this is true, we are happy. Hopefully you will see that. Well, at least we're partly happy. And in terms of the recurrence will work. Because now, if we use this as our rank element, we know that at least 3 over 10 of our data will just go away at every step. So if this is true, we're good. But is this true? And here's a very clever reason. Remember that this element is the median of all the medians. So in particular, among the set of medians, it's in the middle. Right? So its rank among the medians is something like n over 10. So there are, in particular, n over 10 elements that are less than it. Right? So I've chosen those because it's in the middle of it. Each of those elements has 2 elements below it. Because each of those elements was a median. So they're guaranteed to have 2 elements below it. So the median is bigger than n over 10 elements, each of which has 2 elements below it. So it's bigger than n over 10 plus 2 n over 10 elements. It's bigger than 3 n over 10 elements. Conversely, the median is less than n over 10 elements, each of which is less than 2 elements in its own group. So it's less than n over 10 plus 2 n over 10. So its rank is more than 3 n over 10, and it has at least 3 n over 10 above it. So its rank is at most 7 n over 10.
Can you write down the formula?
Sorry?
Can you write down how many it is?
Yeah. So basically, so the element star has has n over 10 elements, medians below, and each has 2 more below. Right? Is it okay if I go to the next page? I know you're all busy scribbling away, so shall I wait a second? Yeah? Okay. So star has n over 10 plus 2 times n over 10 elements below, which is equal to 3 n over 10. And the exact same argument works on the other side. You get the mean. Because then it's going above, each of them is above, you get 3 over 5. Intelligence going to silence dissent that there's turbulence in the firmament. Yes.
So the size of 5, I'm guessing, is somewhat arbitrary,
Maybe.
or the like
Maybe.
dividing everything into 5 elements and finding
Maybe.
using of
Maybe
that.
not.
It's,
We'll see. We'll come to that.
Yeah.
So do you all see what's going on here? This trickery that we're doing. This median-of-medians trick basically allows us to guarantee that the element we pick has a certain rank. And remember, I have not done, the only algorithmic thing I've done is to say, break the array into groups of 5, take the medians of take the individual medians and compute the median. I've not done anything else. All this other reasoning is just conceptual reasoning about the property that element must have. So you have any question about that? Because we're almost done. We're almost at the end of this whole argument. Yes.
How did we get yeah.
Okay.
How did we get the medians of n by 5 thing?
Well, for each group of 5, I can do it in constant time. There are 5 elements, I take their median.
Okay.
The problem is how I get this super median, right?
I mean, n by 5, I mean, say if it's 100, so you have 20 groups. 20 groups of medians. Each, if you add up each thing, you still be getting something, a bigger number.
A big number. How do I find those medians now? How do I find the medians? You're asking how do I find the medians of those n over 5, right? How do I do that?
Split it into 5 more.
Sorry?
Since we know that,
Wait, sorry, show it. Yes.
since we know that there are 5, we can sort them.
No, for each group of 5, I agree. But how do I find the super median, which is the median of all these individual medians? Who said that? Recursion. We just recurse. We already know how to solve the median problem because we're about to find the solution.
Okay.
So the whole algorithm is as follows. Break the array into groups of 5. Find the median of each group of 5. So let me write down the whole algorithm. So 1. Break list into groups of 5. Find median of each group. Find median of medians. Use this as pivot, which means scan the array, find its rank, right? Recurs on appropriate side. This is the entire algorithm. Notice that there are 2 recursions here, not 1. I promised you 1, I'm giving you 2. So if you want to grumble, now's a good time to do it. I'm breaking a list of groups of 5. I find the median of each group. I find the median of medians recursively. I just claimed or proved to you that the rank of this pivot element is going to be good. So when I actually find its rank, whatever it happens to be, it's going to be between 3n over 10 and 7n over 10. So when I do the recursion, I'm not going to have to worry about too much. The set I'm going to recurse on is going to be reasonably small. The algorithm is correct because of what I said earlier. The algorithm will be correct no matter what I picked as a pivot. It would still work. Only question is running time. So the minute I told you about the pivot, the algorithm was going to be correct. The only question now is how long it's going to take. Yes?
Yeah, I appreciate you said a bit more about finding the median of a group of 5. So is this just brute force?
Brute force. 5 elements, I can find the median of 5 elements in constant time. Right? It's 5 elements. I just manually look at them.
Because the 5 is so small, that's why we can claim it's constant time.
It is constant because it's 5.
What if we're 1,000? We'd still claim it was constant?
Yes, if it's 1,000. If it's hardwired. Remember, I can't do that for n elements. Then I would say, okay, break my set into groups of size 1,000, find the median in constant time in each group of 1,000 and then do this recursively. The catch is going to be that the constants are going to get much larger.
Okay.
So in some sense, you want to make that number fairly small, right? And 5 is the smallest. You can't do 3. There's a good reason you can't do 3, but 5 will work. So you want to make, you don't want to spend too much time on this constant size. Okay, what is the running time of this algorithm? So hopefully at this point you can write down the recurrence, but we don't know what the recurrence is going to give us. So let's write the recurrence down. Okay, unfortunately I will have to go to the next page for this. Okay, so T of n, our old friend, is equal to some constant time work to do all this pivoting, scanning stuff, and find all these medians. There are groups of each group, there are n over 5 groups. In each group you spend a constant time, so you're going to spend some other constant times n over 5. Let's say this is to do the groups of each thing, okay? Plus, I have to recurse to find the supermedian. So that's going to take me n over 5, because there are n over 5 medians. Who said n over 10? Someone said n over 10. And there are n over 5 groups, right? Each of them is a median. I've got to find their median. And then finally, the super recursion at the end will be what? I have to recurse on a set. I don't know how bad that set can be, but I know it cannot be bigger than
5.
Thank you. Your name?
Shreya.
Shreya? 7 over 10. Can you explain why?
Because that's the largest number. That's the largest limit for the number to be scanned.
It can be either 700 or it could be 3 over 10. So either way, you believe you're going to eliminate at least 3 over 10, either on one side or the other side. Maybe it'll be more, but we're being pessimistic. And now we have limits. And just for convenience, I'm going to rewrite this as, no, that's not what I'm going to rewrite this as just, you cannot solve this using the Marsh theorem. The Marsh theorem does not know how to handle things like this because it doesn't pattern match nicely. There is a more general theorem called the Akira-Buzzy theorem, which I've linked to in the notes in the class syllabus, that can actually solve this. And it's a bit more involved. But again, my goal is not to tell you to solve these recurrences, but to sort of look at it and say, can I get a vague feeling for what it should look like and then try the answer? And the trick here is to realize, yes, I have 2 recurrences. And yes, they're both, on some fraction of n. But if you look at the, and this is, don't be very careful when you make this reasoning. If you look at them together, there's 2n over 10 and 7n over 10, right? That's still less than n. There's still only 9n over 10. Somehow you've lost 1/10 of your data. You haven't really, but it's almost as if you have. You're not processing the full amount of it. That's a clue. It's not proof, but it's a clue that this is probably going to be a decimation type linear time answer. And then you just plug in linear as your answer and check and see if it works. If you use the Akira-Buzzy theorem, you can actually plug this in directly. It's designed for this kind of recurrence. You can actually solve it. But this is a much easier way to get a feeling for this. And in general, if I had other recurrences, as long as the total of all the recurrences added up to less than, it was some constant times n where c was less than 1, you would still get a decimation number. So, to cut a long story short, I claim this recurrence runs in linear time. You don't have to believe me, you can just check it, plug it in, and you'll see the answer. I would encourage you to do it with the right constant. So what you should say is, okay, assume that. So let's guess Tn is equal to some d times n. Use different constants here. Or let's say it's less than or equal to some d times n. Plug it in on the left side and make sure everything works. That the inequality stays true. But if you plug in this recursively, then you should get the right. Then you should show that when you plug in t of, this is less than or equal to d times n over 5, which is less than plus 7 times d times 7 over 10, dn times 7 over 10, and so on and so forth, you will get something that looks tn is less than or equal to dn. Inductive. So check that please. And that's the idea of reading. That you've done a bunch of recursion. This is a very non-trivial recursive algorithm. But at the end, you are working with a amount of data that is going to be less than n. And that's what we do the decimation problem. And if you quickly do some mental arithmetic here, if you replace all these numbers by what you get for n equal for 3 instead of 5, That first number would be n over 3. The second number would be 2n over 3. And you to work this out. Then n over 3 plus 2n over 3 is equal to n. You get n log n of your norm. You can't have to lose it. It doesn't decay fast. You need at least 1. Well, I said this very fast. You should try it again both sides. What I'm saying is, pretend you're working with k equal with groups of 3 instead of groups of 5. Run this exact same analysis again. See what happens. And again, do it yourself. It's very good to see exactly what happens if you put any. If you put groups of 3. 7 will work, 9 will work, but 3 won't. Okay. This is a clever algorithm. Yes.
I just want to make sure, like, I'm trying to think concretely about how I program it. So, when you want to throw away 3/10 of your collection, you have to figure out some way of iterating through the array such that you never land on the 3/10.
Right. So what's going to happen is that once you pick your pivot, like I said, an inefficient way to do this is to scan the array to find the pivot rank. Now you know that there's so many elements below the pivot, so many elements above the pivot. Copy them into a new array. So scan the array again. Whenever you see an element below your pivot, put it in the first part. Whenever you see an element above the pivot, you know where to start from. And you maintain 2 pointers. So you fill up the entire array, the new array you have. Now you know everything is segregated. Now when you run your recursive algorithm, you just give it the pointers to the start and the new array.
When I hear you say copy, then that's almost linear, but
it's linear.
It is.
That's what I'm saying. It's inefficient, but in one case, yes, it's not expensive.
I see what you mean.
But you could be more clever and do it in place by just sort of saying, okay, I know that when I scan this, I just do swaps. So basically, I have the first element, I have the next element. If it's less, I swap it and put it there. If it's more, I swap it and
that makes sense.
And then you can do it in place. You won't have to spend that extra. That's why I said I was being inefficient, but they're all linear.
There you go.
Yeah. Okay. And in fact, if n is not too large, sorting is actually possible. Because of all this extra bookkeeping and all this recursion. So if n is very small, just sort it. It's fine. If n gets really large, then this thing starts beginning to win. Because there is initial overhead for doing all this work. So it doesn't win from day one. It wins when things are large enough. And that's, you've seen this in practice, right? Bubble sort is great if you have small numbers. You don't have to do more sort of all the small numbers. Recursion adds overhead. Yes?
How do you pick the 5 elements? You pick the first 5?
The first 5, arbitrary. I made no assumption about the groups of elements. That's the beauty of this whole thing. I didn't care about them at all. So just the first 5, the next 5, the next 5, then you can do the array index mod 5. Or the index divided by 5. So take the integer value. So you just have groups. So you can even do that in place, right? You do the first 5 elements, find this median and rearrange them. Take the next 5 and then keep doing that. So yeah, there are issues with how to manage this efficiently. None of that will change the asymptotics of it. And that's what I'm trying to sort of basically explain.
None of them will change asymptotic what did you say?
Running time. The asymptotics of the behavior will not change at all. Okay. It is now 38. Let's take a 2-minute break and then we'll move on to the next phase. Okay? So let's take a 2-minute break. You come up now. You all know the ball.
When he starts teaching dynamic programming and video algorithms, he's trying to make it better. क्योंकि वो पार्ट मेरा बहुत ज़्यादा बैठेगा ना क्या? कैसे भी तो बैठेगा ना? बैठना पड़ेगा या रिकॉर्ड क्यों करेगा? हम लोगों ने काम डिवाइड किया ना वो लोगों का सीधे का काम अलग करने के लिए ऑफिस आवर्स लेने के लिए इसको बोला मैं रिकॉर्ड कर दूँ फिर हम ट्रेडर्स में हम तीनों इक्वली डिवाइड करेंगे ये मैं अच्छा मेरा काम मैं टी आवर्स का काम सिर्फ ईमेल से करूँगा, जैसे किसी ने बताओ ईमेल से भेजा तो मैं उसका डाउट किया, ऐसे ऑफिस आवर्स अलग से नहीं लेता। काम ज़्यादा नहीं रहेगा ना करने के लिए, ईमेल से रिप्लाई करो, कैनवस अपडेट करो, कैनवस पे फिर एक बोले तो नहीं अपडेट करूँगा इतना ही काम
अभी मेरी पुरानी मेलिंग लिस्ट है, मेरे पास इतना टाइम नहीं है मेरे पुराने, इसलिए ना मेरे मेल से
then you will get some number which will be less than so just do the so okay, so yeah. Because you're using induction. You're saying inductively that's assumed. So I can plug in the groups. I think when you so you're doing inductively. So basically the possible way to do it is just by one yeah, it has to be the same key. You can't just say that. You don't want to say that TMN is listening to CMN is then I end up with TMN is listening to therefore it has to be the same person. Why you're otherwise your process is not better. So I was going to move on to the next topic, but I think there's some confusion. Not confusion, good confusion. Okay, about why the rank is in fact 3 over 10 and why this comes. Okay, so let me just quickly go this together. I break my input into groups of 5. Okay? In each group of 5, I find the median element. So far, so good. I find the median of the medians. Again, so far, so good. We're not worried about time. The claim that C is non-trivial here is that the rank of this element is reasonably large. It's at least 3 over 10, but it's not too large. It's at most 7 over 10. And again, the argument is the following. In order to show that the rank of an element is at least something, I need to show that there are at least some number of things that are less than it. Right? If I want to show this element is at least the second min, it's not the minimum, I need to show there's at least one element below it. Same thing here. So in order to prove this claim, I need to show that there are at least 3n/10 elements that are below it that I picked. And I have not sorted the area. And the reasoning is as follows. This element star is bigger than n/10 elements by virtue of being a median. So it's in the middle. There's a whole bunch of medians here, it's in the middle. So there's n/10 elements below it. But each of them has 2 elements below them because they were the medians of their individual groups. So this element here that we picked has 3n/10 things below it. It could have many more. I don't care. It has at least 3n/10. That's all I care about. That its rank is at least something. But now if I flip it around, it's below a certain number of elements. Each of them has something below them, so its rank is at most something. So it's being pushed from both sides to be in the middle. And that's exactly what we want in this element, that its rank is in the middle. Does that make sense to everyone? Here are all things you need to mull over. Like about 36 hours from now, it's like, it all makes sense. I was trying to solve a problem the other day, and I was stuck. It took me 3 days, and I was just pondering. And finally I gave up and went to bed. I turned the light off, I went to bed, and boom, I got the answer. Then I had to get up for another half an hour and write it down. Yes?
So if we were to increase the group size from 5 to 7 or some arbitrary number, would that, my guess is that would take the T 7/10, that would make a smaller number, but would increase the size of C.
Yes. And at some point,
it stays linear time.
Yes.
No matter what you do.
Yes. Okay.
So you do a little bit of optimization there, but not.
You can, but not much. Okay. Time to move on. Okay. And again, use a discussion forum for more questions. This is all I'm going to tell you about dividing numbers, at least in its current form. We've seen the basic strategies. We've seen how to plan a line of attack on a problem by imagining what your recurrences look like. We've seen the different flavors of recurrences. The homeworks will help you work out more of these examples. And again, I encourage you to use the resubmission option. The goal is to get you to understand, not just see how well you can do on a quick answer. As long as you get, if you can go through this and really understand how to do this, that's a good thing. And if you all get full marks in homework, that's a good thing too. There are other ways to distinguish between grade. But dividing number only works up to a point, right? And recursion only works up to a point. And as you've been observing, it kind of works when things split off nicely. It doesn't seem to work as well if things don't split off nicely. And so let's take our favorite example of a recursion that isn't a good recursion, namely computing Fibonacci numbers. And we all know what the reference for Fibonacci number looks like. F of n is equal to fn minus 1 plus fn minus 2. F of 0 is equal to 0. F of 1 equal to 1. And a cool little trick I learned a long time ago is if you want to convert from miles to kilometers, just assume if the miles is one Fibonacci number, the kilometers is the next one. It works very well, approximately. There's a good reason. 5 miles, 8 kilometers, 8 miles, 30 kilometers. This is a recursive definition. And therefore, as a recursive definition, we should be able to analyze whether running time is going if we had to compute this in the way described. The problem with this recursion is that it's not a nice divide and conquer in any sense of the word. Right? You're repeating over n minus 1 and over 2, n minus 2. And although the master theorem once again fails to tell you how to analyze this, there are notes that I've pointed to in the class syllabus that tell you how you analyze a recurrence like this. And in fact, this recurrence would, roughly speaking, would take you something like this time to solve, where phi is equal to 1.618. It's basically what is square root 5. Anyone?
Minus 1.
Square root 5.
1 to 2? Yes? Okay.
Something like that.
This is exponential time. It's a constant to the power of n, which is really, really silly because you all know you can compute Fibonacci numbers faster than that. The reason you all know you can do this faster is because this recursive formulation, if you implement it as it is not being very clever. Yes, it's using recursion, but it's using it in a very stupid way. Now again, the point is not to know the answer how to do this. The point is to understand why this is wrong. This is wrong because if you look at what it's doing, it is doing lots and lots of work over and over again. When you compute fn minus 2 there, you are going to compute it again when you compute fn minus 1 without realizing that you've already done it. And if you in fact look at how many times you're going to compute f of 1, it's a pretty horrible number. It's in fact these many times. So it's hardly surprising that your running time is going to be this because you're computing f of 1, which is 1, many, many, many times over, independently for all these recursive steps. And that's because while the recursive approach to thinking of if I knew more volume from that, I actually did not see who had that phone, so don't worry, I don't know what to do. Next time choose a better recursive. So the problem here is not the recursion you shouldn't do recursion. Recursion is good. But blindly using recursion to guide the algorithm strategy, which is what we did with divide and conquer. We said, oh, well, we'll write the recurrence, it's great. The recurrence will tell us how the algorithm works. It's not going to work. The recurrence is not telling us how the algorithm works because the algorithm is horrible. This brings you to the sort of the next level of recursion, namely dynamic programming. The idea that you should think recursively to design the solutions problem, but you don't implement it the way it's stated. So let's go back to this problem. Our observation is that if we write down the recurrence for this, we're going to compute f of 1 many, many times. We're going to f of 2 many, many times. It's a waste of effort. And we know this how? We know this because how many different subproblems are there in this recursion? If you want to compute the Fibonacci number n, how many different numbers do you need to keep track of? You need to keep track of the number of Fibonacci n minus 1, n minus 2, n minus 3. There are n subproblems. So so if you look at, say, a divide and conquer recurrence, right? It looks something like this. You start here, you have some input. Then you break the input off into pieces, right? So there's one piece goes here, there's one piece goes here. And you break this off, and there's one piece goes here, and there's one piece goes here, and then you do some more recurrence. And this is, in fact, your entire input right there, right? This is what a divide and conquer recurrence is. But in dynamic programming, if you write down the subproblems, which are here, a small number of them maybe, your recurrence is causing each of them multiple times. It's causing this, and this node is causing this too, and this node is causing all of this. That's an unholy mess. Right? And that's what we have to fix somehow. That we know we don't have to do too much work. We know that there aren't that many subproblems that we care about. But somehow we're using them over and over and over and over again. And of course, as many of you are computer scientists, you know that if you're doing something over and over again, you should store the answer. So you don't have to do it over and over again. Just record it somewhere and look it up if you need to. This is a very basic trick in computer programming, right? And so that's what dynamic programming is all about. At least initially, at a first level approximation, this is what dynamic programming is about. A simpler version of dynamic programming is called memoization, where it says just store your answers. So if we had to rewrite our Fibonacci sequence calculation with the idea that we should store answers, we'd say something like, how would you write this? So we create some array. So create some array here. We create some array of size n, right? And we initialize. It's not me. Someone has to go. No, not me. Whoever it is, please figure it out and turn it off. Good. And then we say something like, if we want, when you want to compute, so suppose you want to compute Fibonacci of n, right? We first, okay, someone help me. I'm very bad at writing code online. I would fail a Google interview like in the first 10 seconds. So, someone, anyone? Someone?
If n is less than 2,
okay.
then
Okay, sure.
return it.
Well, oh, I see. Okay. Well, can I use the area that we just created?
Oh, sorry. Yes,
Yeah.
of course. So,
Hold on.
like if
I have nifty tools here. Gotta use the tools, man.
yeah, I guess if that element in m is valid, use it.
Yeah, so let's say mn is set to all -1s, for example, right? So let's set them all to -1. This is why we fail to Google it.
There you go.
Yeah.
Or null.
Yeah, or something like that. I don't know that, but yeah. So if mn, please don't write my code. I'm ashamed of myself. So if mn is greater than 0, return it, right? Right?
Or equal. I guess one of them will have 0 in it.
These are all very good optimizers. So okay. Else, do what?
Else, call the recursion.
Sorry?
Call the recursion.
So then
fn
set mn equal to
f of n
yes
plus f.
Something like that? More or less? I won't get a call back for a second round for sure. So what we're doing here is not very different to what we did before. Instead of just saying return fn minus 1 plus fn minus 2, we said, well look, if you have the answer, just return it. There's one little step that makes all the difference. Because now you've recorded it. And so you won't keep doing this recursion. The recursive analysis will break down. And in fact, you could look at this and say, well, this is a rather silly way to implement the algorithm, because I can unroll the recursion entirely. Right? Because what I'm going to do is to compute f of n, my new method will say something like this. Again, I hope you're not, I'm going to change, like, we don't want to write this one. It's really terrible. So my new f of n will say something like, I've initialized the area appropriately, right? For I equal to 2 to n, and I is equal to something like this. Again, it's not quite basically. And there's no recursion anymore. We've unrolled the recursion entirely. So this is one of those things where, so the way I like to think about dynamic programming, as opposed to divide and conquer, is that just like with divide and conquer, you think recursively, but you implement it bottom up. So the design principle is the same, but you don't take the algorithm literally. With divide and conquer, the whole point is that you would just design the recurrence and they would just work immediately. Here you have to design the recursion, but you have to unroll it, because somehow the recursion by itself is doing too much work. So think top down, because that's easy for us to think that way, but implement bottom up, which is what we did here. We went from a purely recursive to a recursive memoization to a purely bottom up unrolled strategy. And so when you look at how a dynamic programming algorithm actually looks, you look at the code, it will look a little strange. Because it might seem like, why is this working? What is it doing? And the answer is because what you end up writing is not how you thought about it. You thought about it recursively, but then you unrolled it to make it work. And we're going to see in the next lecture, and I have notes on this you should take a look at before next time, many examples of how this works. This is a very simple example where the number of subproblems themselves is in fact a small number. That's a clue that dynamic programming should work. So one of the hardest things you will find is how to recognize when a problem requires a dynamic programming solution. One clue is that the number of sub-things you need to keep track of is very small. It's a polynomial number, or linear, or n squared. So you just have to keep track of them. You will find though that there are problems where the number of subproblems is exponential. It's not linear. So you can't actually do something like that in programming. But the number of good solutions that you care about will itself be profound. So there are many levels of complexity we're going to start adding on to our basic recursive strategy. So we're still recursive. We still want to be recursive. But it's going to get more and more complicated as we go on. But they'll all follow this basic idea that you think recursively, look at the algorithm, unroll it, and then implement it more. And that's how dynamic programming basically works. Okay? And I should say that, anecdotally, this happens every year now. I get feedback on this, that this is the questions that all these companies use to test. They use dynamic programming questions to test whether someone's going to go to the next level of interview. I don't know why, but these are the ones that people trip on a lot. So this is going to be important, not just for the job, but also because it's another way of thinking about it. Okay, so please read the notes on dynamic programming that I've linked to in the class page. Another minor note, tomorrow's a drop deadline, and I know many of you have been asking me what's going to happen. Right now, there are actually 3 open slots, and I have a wait list that's been formed. Some of you have been emailing me. So some of you already got emails saying that there's a good chance you're going to be in the class because of that. For the rest of you, just wait till tomorrow and we'll see what happens. All right, any questions before you?
Did you say there was you can submit each homework once for review or just once?
No. The homework will be broken down. And you can do, think of it as a problem by problem now. Each problem can be used for review. And